Okay, well, let's get started. The irony of anyone being late for a lecture on time travel is not lost on me, but we'll start nonetheless. Okay, the topic today, first of all, by the way, my name's Rob. I'm a particle physicist based mostly at Royal Holloway, University of London. The topic we're talking about today, broadly speaking, is special relativity. So this is Einstein's theory that brings together themes of light and space and time, and teaches us that these two latter concepts, space and time, are not absolute. You know, the name relativity, all things are relative in space and time. So we're going to build up the theory, how this was motivated, because some of the ideas are extremely bizarre, but you know, even in the most theoretical of theoretical physics, these ideas don't just come out of a vacuum, they don't come from nowhere. There's a history and there's a context that leads Einstein very nicely towards his postulates, which are very simple, but when taken to their conclusion, give us some really quite remarkable and very bizarre, give us a very bizarre new understanding of how the world works. But again, the most bizarre thing, as I said last week when we spoke about quantum mechanics, the most bizarre thing is not the theory itself, but it's the fact that the theory is true. It's the fact that it works, and this really is how the world behaves, in this very counterintuitive way, this way that is completely sort of alien to us in our everyday lives. It's not something we experience firsthand, you know, some of the phenomena we're going to discuss, but again, it really is the way the world behaves. We've done experiments, you know, our modern theories are based on these insights that Einstein had. And most importantly, we've tested these things, okay? So here's a rough outline of what we're going to talk about. So we're going to start actually very basically, and I'm going to take many of you back to the physics you would have done in school when you were 13 or 14, and we're going to talk about Newton's laws of motion. We're then going to talk a bit about Galileo and Galileo's first kind of stab at this idea of relativity. We're then going to move forward a couple of hundred years to talk about the theory of electricity and magnetism, developed by, most notably, James Clerk Maxwell, a Scottish physicist in the late 1800s. And then moving on from that, this really is the kind of the final nail in the coffin for Galileo's theory of relativity, and prompts Einstein to develop his own theory of relativity. And then we're going to talk about some of these effects that relativity describes to us, the most bizarre of which is this idea of time dilation. We'll come on to it, but the fact that the passage of time, again, is a relative thing. You know, 1 second for me is not necessarily 1 second for anybody else. Length contraction, again, this idea that space is also a relative thing. When you measure a length, this is a description of how far in space one end of the object is to the other end of the object. This is also a relative construct. And we're going to apply these two ideas into a problem called the tunnel paradox, or the train paradox, which brings together these ideas of time dilation and length contraction in quite a nice way. And there'll be plenty of time for questions throughout as well. So we probably will have a bit of a longer Q&A session at the end, just because frankly, it was a busy week and I didn't have time to prep a huge number of lecture slides, so we'll have lots of questions, but we'll also have questions throughout, okay? Okay, so let's start with Newton's laws of motion. So Isaac Newton, obviously an extremely bright chap, alive in the sort of middle of the 17th century through to the early 18th century, he develops and publishes in his Principia Mathematica 3 laws of motion. So these laws of motion, despite being very old, despite being part of classical physics, which again last week we summarily dispensed with, these are still the laws of motion that we use to, you know, launch rockets, to build bridges, to make all sorts of mechanical structures, and they still work extremely well. Okay? They're very simple, but we can apply them to even the most complex mechanical systems. So the first law, there are 3, the 3 laws of motion. The first law simply says that an object will not change its motion unless it is acted on by a force. So, for example, if we have Isaac out here in empty space, if he takes his apple he throws his apple at some speed. His apple will keep moving along a straight line forever and ever until it hits something or until it's acted on by a force. Okay? So until it's pushed, and it then might change its direction or change its speed. But until it's acted on by a force, it will keep moving forever. Now, you might think, well, if I kick a football across the floor, the football doesn't move on forever. It eventually stops. I'll come to you in a minute, yeah. But this isn't the case that, the football gets tired and it sort of just decides to lose its motion. The football is acted on by a force. It's acted on by the friction on the ground. Now, if you kicked a football in completely empty space with no gravity around, no air particles, nothing that can cause drag or resistance, it will just move forever in the same direction in a straight line. Okay? That's what Newton's first law says. Yeah, did you have a question?
So yeah, the football is, so depends on the surface it's running on, also makes it different to how quickly it will stop.
Absolutely.
Yeah, friction is going to slow it down.
That's exactly right. Yeah, if you kick it on like an icy surface, it'll sort of slide for a long time. But if you kick it on a carpet, what's it going to do compared to the ice?
It's going to slow down quicker.
Exactly. Yeah, because there's more friction, right? Yeah, very good. Any other questions or thoughts at this point? No? Okay, super. So the second law, Newton's second law, this is his very famous equation, F equals ma, force equals mass times acceleration. This law just tells us that the harder you push something, the quicker it speeds up. Okay? So Newton applies a force F to this block or this cart that has a mass m, and it will have an acceleration a. Now acceleration, we kind of understand intuitively, it's how quickly you speed up. So if you're thinking about a car, it's like how quickly you go from 0 to 60. Okay? For example, this car here, if Newton puts his foot on the brake and a force F is applied by the engine, the car goes to 0 to 60 in 8 seconds. Okay? Now, if he applies a force 2F, if he applies double the force, he'll get double the acceleration. And so now the car goes from 0 to 60 in 4 seconds, as opposed to 8 seconds. Okay? The third law is one that's quite commonly misunderstood. This is often stated in a sort of quite, in a way that you can, think of in lots of different ways in your life, and in a way that has sort of maybe a more symbolic meaning, as every action has an equal and opposite reaction. You might say this as a sort of karmic phrase, talking about if you do good deeds will come to you and whatever. But it's really a quite technical thing about forces. So if Newton pushes on a block to the right with a force F, then the block pushes back on Newton with the same size force, but in the opposite direction. Okay? This is the principle that allows us to shoot rockets up into space, because when you ignite a rocket engine, the rocket engine pushes down on the Earth with a very large force, and Newton's third law says the Earth pushes back up on the rocket with the same large force in the opposite direction, and so the rocket lifts up. Okay? Okay. Any questions about Newton or Newton's laws so far? No? Okay. So, to Galileo. Now, the thing here, we've done the chronology slightly the wrong way around, but I think it makes sense to talk about it this way. Galileo was actually died about the same year that Newton was born. So Galileo precedes Newton. He doesn't know at the moment about Newton's 3 laws of motion. But in a book he publishes, 1632, so this is 10 years before Newton is born, he describes his concept of relativity for the first time. When he does this, he's thinking about sort of people on a ship, someone below the deck of the ship, which has no windows, and he makes the note that someone who lives below the deck of the ship can't tell whether the ship is in the port, not moving, or whether the ship is moving across a very calm and gentle sea. Okay, that's sort of the key concept he latches onto in his description. So we're going to try and illustrate this idea by imagining 2 people, Alice and Bob, and these 2 will recur throughout. Alice has a tennis ball, and she's going to throw the tennis ball at Bob. Okay? So Bob is an observer located at a different point in space to Alice. Okay. So Alice throws the tennis ball at Bob. It leaves her hand at 5 meters per second. And if we ignore air resistance, we assume it continues to move towards Bob at 5 meters per second. So from Alice's perspective, in Alice's reference frame, which is a phrase we'll use quite a lot, the ball moves with 5 meters per second. And also in Bob's reference frame, the ball moves at 5 meters per second towards him. Okay? So these two people, they're stationary, they're not moving relative to one another. They just throw a tennis ball, the other one catches it, it leaves her hand at the same speed it reaches his hand. Okay? So this is simple. What about if Bob was moving? So if Bob runs towards Alice at a speed of 2 meters per second, again, from Alice's point of view, the ball leaves her hand at 5 meters per second. But from Bob's point of view, first of all, in his reference frame, he is not moving. Okay? It's like if I run across the room, I myself sort of am the center of my own little world and my own little perspective on what is moving and what is not moving in the world. From Bob's point of view, it looks like Alice is moving towards him. And additionally, it looks like the tennis ball is moving towards him even quicker than Alice threw it. So it looks to him to be 7 meters per second. The reason being that we have added those two speeds. Okay? So the speed of Alice apparently moving towards Bob as he really runs towards her adds to the speed of the tennis ball, and so the tennis ball hits his hand at a higher speed. Okay? So the question is, who is correct? Well, no one is incorrect or correct in this scenario. Alice makes the measurement in her reference frame, and for her, that is how fast the ball is moving. It's moving at 5 meters per second that way. Bob makes the same measurement, or he attempts to make the same measurement in his reference frame, and he finds that the ball is moving at 7 meters per second. Again, he's not wrong. There's no ultimate arbiter of how fast the ball is moving. If you ask Bob, it's going this fast. If you ask Alice, it's going this fast. Ultimately, the speed of the ball is relative. We can't say for sure, there's no absolute truth of how fast the ball is moving. It's a question of who you ask and how they measure it. Okay? Yeah.
Because we're not asking about their point of view, we're asking how fast the ball's going. But it is going 5 miles per hour. But it's just because it's moving and going 7 miles per hour. So technically Bob's wrong because it's going 5 miles.
Okay, let me pretend for a minute that these two, this little box I've drawn here, this is not just the box sat on the earth, this is a moving train. Okay? So this whole thing is moving. This experiment is going on a moving train. So Alice is stood still on the train, Bob is running up the corridor of the train, and someone is sat on the platform outside of the train. Let's call them Sarah. Okay? So Sarah sees the train go past at, say 20 meters per second. And she sees, Alice still on the train, also moving at 20. And she sees Bob running up the corridor, now moving at 22 meters per second. And she sees the tennis ball going at 13 meters per second in the other direction. So not only is the tennis ball doing at a different speed, it's going the other way. Okay? The train is moving to the right, the tennis ball appears to be moving left, even though Alice threw it to the right. So now who's right? There's a third person. And there's someone who's on the moon, when the moon is spinning around the Earth at extremely high speeds. And he looks, with an extremely powerful telescope at how the tennis ball is moving. There's all these people moving at different speeds. They all have different opinions about who's right, how fast the ball's moving. How do we say who's right and who's wrong? I don't know. We can't, because there's no right answer. Okay? It depends who you ask. There's no such thing as absolute velocity. It's all relative. Depends who you ask, how fast they're moving, where they are, etc. Okay? Have I convinced you?
Because if you put a speed meter on that telescope,
Yep.
if you throw it, it would measure how fast it's going. So technically it doesn't matter how someone else sees it. So if I throw a telescope right now,
Let me interrupt. What's a speed meter?
let's say it's just a speed meter.
but what is a speed meter?
Speed.
But that's cheating because that works by measuring how many turns the wheels do against the road, again, relative to the road. So imagine I put a car on a treadmill and I spin the car's wheels and I get the car going at 30 miles per hour on the speedometer, but the car's on a treadmill, it's not moving anywhere if I stand next to it. Okay? Trust me. So there is an exception. So there's no such thing as absolute velocity, but there is absolute acceleration. Now, because if you think about it, if you're in a car and you put your foot on the accelerator, you feel yourself push back into the seat, don't you, when the car speeds up? So that is something you can measure, and that is something you can say inarguably is happening. Well, I know I'm accelerating forwards because I felt myself push back into the seat. But if you're traveling along the motorway, you know, if your parents are driving you somewhere and you're going at a constant speed, you can't tell really, if you close your eyes, am I moving or am I not moving? Obviously, you hear the sound of the car engine and you might look out the window. But if you're moving at a constant speed, you actually can't tell. You know, you can't do an experiment that will tell you I'm moving or I'm not moving. Okay? Accelerating is different, but constant speed, there's no change. Okay? Any other questions at this point? Yeah?
Can you help me understand the difference between velocity and acceleration, please?
Yeah, so velocity is how far you move per second. So if you're traveling in your car at 30 miles per hour, in 1 hour you'll move 30 miles. Acceleration is how fast you pick up speed. So for example, your car might go from 0 to 60 in 8 seconds. In that case, your acceleration is, well, it's not a very good unit, but you know, it's 0.75 miles per hour per second. No, sorry, 7.5 miles per hour per second, or something like that. So it's telling you how quickly you gain speed per second.
So once you get to a place where you're not gaining speed anymore, technically the measurement is of velocity again, like once you're cruising.
Well, they're independent measurements. They're different things, acceleration and velocity. So your car doesn't have an acceleration meter on it. It just has a speed meter that tells you how fast you're going. But if you look at how quickly your car's speed dial goes up, if it goes up, vroom, straight to 60, that's a high acceleration. You've gone up to high speed quickly. If it takes a very long time, if you're in an older car and it goes very slowly up to 60, that's a lower acceleration. Okay? Any other questions at this point? Yep.
Going back to what he was saying about the speed meter.
Yeah.
Surely if you were in the train and you did it, it would take 5 miles. But if you were outside the train, it would do it faster because obviously I had to take into account the train and the ball going.
What, sorry, say again, explain again.
Cameras and you're inside the train.
Yeah.
It would do 5 meters per second because you're inside the train. You're not as far as the speed.
So if you're measuring the ball speed inside the train.
But if you're outside the train, it would do it faster because obviously it will take the train into account and the speed of the ball into account.
Exactly. So who's right? We get a different answer, right? We get a different answer for the speed depending on if you ask someone outside the train on the platform or someone inside the train who's, you know, sat down on a seat looking at the ball come towards them, right?
What happens if you just throw the ball in the air and you're not?
We're going to talk about that in a minute. Yeah. Okay. Yeah. Next question. Up the back. Yeah.
What if you throw the ball
Yep.
the same speed as the train's going? So let's say the train's going this fast.
Ah.
And you're inside the train. You're throwing it at the same speed as the train's going.
Yep.
Does that mean inside the train it would be going, let's say, 20 miles per hour? But if you're outside, it would just be staying still.
Absolutely. So if the train goes past at 30 miles per hour to the right, I'm on the train and I throw the ball to the left at 30 miles per hour, someone on the platform will just see the ball, oh, it's there, it's fallen down. You know, they won't see it move horizontally. You're exactly right. Yeah? Does that make sense? Any more questions before we move on? Okay, super. So, this is the idea that this is a relative phenomena, okay? Now, let's talk about a train some more. So let's suppose now Alice and Bob. Alice is on the platform. Bob is on the train. The train is moving past the station at 20 meters per second. And Bob throws the tennis ball upwards. So we're thinking about this right now in the red box. I'm thinking about this from Alice's point of view, okay? So when Bob is holding this tennis ball on the train, it passes by Alice also at 20 meters per second, okay? So the tennis ball goes up. The train moves to the left. and the tennis ball comes down. So for Bob, who is in the train, the tennis ball just goes up and comes back down. It doesn't, for example, hit him in the face, okay? You know, if you're traveling at constant speed in your car and you drop something, you know, onto the passenger seat, it just falls straight down from your point of view. It doesn't swing back and, you know, fall into the back seat. It just falls straight down, okay? And if we think about what Alice sees when she looks at this process, she actually sees the ball move on a sort of curved trajectory, on a parabolic path. Because again, if you think, you know, when Bob initially threw the ball up, he was over here. When the ball landed back in his hand, he was some distance to the left because he's on this moving train. So Alice perceives the motion of the ball to be that of a projectile, something that is sort of fired, you know, at an angle that goes up along a parabolic path and lands back down. But from Bob's point of view, the ball goes up and the ball just lands back down, you know, on his lap as if he wasn't moving. Okay? Now, the key thing is that what we've said here is for a train moving at constant speed, okay, for a non-accelerating train. The train was initially at 20 meters per second, and it was still at 20 meters per second when the ball landed on Bob's lap. If the train is accelerating, this changes things. So now Bob is on a speeding up train, a train that's going from, say, 0 to 60. He throws the ball up, but the ball swings over the top of his head and lands on the floor beneath him. So this is a different observation than Bob would make if he was just sat still in the platform, okay, if the train wasn't moving. The acceleration of the train leads to a different consequence, okay? So Bob knows he's accelerating. He knows his speed is changing, okay? But if we go back to this case, you know, where the train is moving at constant speed, if you imagine all the windows are completely blacked out and the engine makes no sound, Bob's trying to do an experiment to figure out how fast am I moving. Well, he throws the ball up, the ball lands in his lap. That's the same thing that would happen if the train was just in the station. So he can't tell how fast he's moving by doing any experiment, okay? Yeah?
Alice's reference frame though, wouldn't the ball go like up and then go to the side a bit, but then
Which one are you talking about, the constant speed or the accelerating?
the accelerator?
Oh, the accelerating one.
So Bob would accelerate,
Uh-huh.
so would the ball. So the ball would also go in the same direction as the train, but then land relative to Bob behind him. So it went in different directions relative to the two frames of reference.
Well, yes. So for someone who stood on the platform, the ball ends up further to the left than it was before, right? Because the ball goes up, the ball is in the train, and so the ball lands further to the left. But the train is accelerating and Bob is accelerating, so he lands further to the left than the ball lands. So from his point of view, it looks like the ball's gone behind him because he moved further than the ball did. Now, the reason the ball doesn't move as far as Bob does is that when Bob lets go of the ball, he removes the force that he's providing to the ball that's keeping it accelerating. Remember back to Newton's second law? Force is mass times acceleration. To get an acceleration, to make the thing change its speed, you need to apply a force. Now, if Bob throws the ball up, there's nothing touching the ball when it's in midair, and so it stops accelerating. It keeps going at the same speed it was going at when he threw it up, but he's getting faster because he's on the accelerating train. You know,
So it lands behind.
yeah,
So in Bob's point of view, it lands behind him.
yeah, yeah.
But to Alice's point of view, it lands in front of where he used to be,
That's exactly right.
but then still lands behind him.
That's exactly right. That's exactly right. It's because his position has changed. He's gone further to the left.
They both moved.
Yeah,
To Bob's frame of reference, it went behind him.
yep.
To Alice's frame of reference, it still went behind him, but Bob also moved, so it went forwards as well.
Exactly. They both moved forwards, but Bob moved forwards more. So it looks like it's gone behind him. Yeah, that's a great question. Yeah. The back?
What would it look like if you would have to be a very fast runner, but if the train and the ball was moving at a constant speed, then we're talking about Alice's reference frame.
Mm-hmm.
What if Alice is running at 20 meters per second? What would she see?
So she would just see the ball go straight up, straight down. Yeah, it would look completely the same to her if she's moving alongside the train. Yeah. Yeah, one more at the back, yeah.
You know, if it's at constant If you throw it up, it looks like it's just going up and down.
Mhm.
If we go back to where there's no gravity, it always goes. If
Mm.
if I threw it up here, if it like just stayed there, because it would stay there if it was going that way, right? But if you're going up, what would it just stay in the air in that aeroplane?
It would do. Yeah, if you threw it up and you were going up at the same speed that it was, well, I mean, in a sense, if you're in a rocket that's moving up at a constant speed, if you throw the ball, you're giving it more speed than the rocket, so it would move up. But it would move up at a constant velocity. So if there's no gravity, it would just keep moving up. Now, the interesting thing, so you're beginning to touch on the thing that allowed Einstein to develop his general theory of relativity, which is much more complicated, so you're getting way ahead of me. Now, imagine you're in empty space in a rocket. So think about, remember, the train is in the station, not moving. The train is pulling out of the station, or the train is moving along at a constant speed. We can't see any difference. We don't notice anything inside the train compared to when the train is not moving and when the train is moving at a constant speed. The ball goes up, it lands in my lap, just the same whether I'm staying still or moving at the constant 20 meters per second. Now imagine you're in a rocket. You're away from the Earth, you're away from any source of gravity, you're floating weightless in space. Okay? Now, suppose your rocket starts accelerating vertically upwards, whatever upwards means in space, but it accelerates at precisely 9.81 meters per second per second. What's going to happen is your rocket accelerating up is going to sort of catch up with you quicker than you can move up with it. So it's going to feel like it's coming up at you, and you're going to feel a force pushing on your feet from the floor of the rocket. Now that force feels exactly the same as if you're just stood on the Earth, in the Earth's gravity. So now you ask the question, well, am I in an accelerating rocket, moving up in empty space with no gravity? Or is my rocket parked on a planet, not moving, not accelerating, that has a gravitational force pulling me down? And now Einstein says you can't tell the difference. So he extends this idea of relativity to acceleration and gravity. And he says there's no way to distinguish, at least locally, meaning if you have a small enough rocket that's not huge, where there will be differences in the gravity. If you have a small enough rocket, there's no way to tell the difference between gravity pulling you down or acceleration of the rocket moving up away from you, making it feel like you're in a gravitational field. And that's the sort of foundation of his theory of gravity, which we'll talk more about next week when we talk about black holes. Okay. Anyway, we better move on. Okay, so what are we talking about? We're talking about acceleration. Okay, yeah. So the idea that this train that is moving at a constant speed is indistinguishable to a train that is not moving at all, is moving at zero speed. Any experiment you do on it will look the same. Throwing the ball up, it still lands in my lap, just as it would if the train was not moving. There's a special name for this kind of reference frame that is non-accelerating. We call it an inertial reference frame because it respects the law of inertia, which is Newton's first law, which is unless I push something, it doesn't accelerate. Okay, the ball does not accelerate left or right, whether I'm standing still or whether I'm moving on the train, because there's no force acting on it. Now, an accelerating reference frame does not sort of respect this law because, as we saw here, if you are Bob, this is getting a bit beyond what I wanted to talk about, but if you're Bob and you see this ball leave your hand and go up over your head, what might you conclude about the ball? Any thoughts? Yeah?
Could you could you conclude that the train is moving fast, like it's accelerating because you know the ball's going over your head?
You might conclude that. There's another thing you might conclude as well.
That there's a force acting on the ball.
Exactly. If you see the ball leave your hand, move up over your head, change its motion, and land behind you, you might conclude there must be a force acting on the ball. But there isn't. There is no force acting on the ball. There's no horizontal force pushing it left or right. Okay? It's not that the ball is actually accelerating backwards. It's that you're accelerating forwards under the ball. You give the impression that the ball is forced over your head. Okay? This is something called a pseudo-force. that arises from a non-inertial reference frame, which just means an accelerating reference frame. So another really good example of this is the centrifugal force, which you're probably all familiar with. You know, if you go around a roundabout, you feel like you're being swung out to the far side of your car. The truth is you're not being swung out. Your car is accelerating inwards away from you, and it gives the impression of you being flung out. So it's a pseudo force. It makes it feel like there's a force swinging you out away from the center of the roundabout, but really the car is just accelerating in away from you towards the center of the roundabout. Okay? Yeah?
You know when you said if it's at a constant move, if you dry up, it will just land in your lap.
Yeah.
But wouldn't that be an exception if, let's say, the roof was gone? If you throw it up, it would be different. Because if you're, I don't know how it works, because if you're in a box and moving, at constant move, you can throw something up and you can catch it and go up and down. Whereas there's a missing wall, roof or something, then it will move.
It might dash off behind you. Yeah, so that's because of the air. So if you did this in a zero air environment, like on the moon, no matter how far up you threw the ball, pretty much, you know, even outside the roof of your car, it would still move along with you and land in your lap. But the reason that that doesn't happen on the Earth, if you have like a convertible car, is that outside of the roof of your car, the air is rushing over the top of your car at high speeds, and so the air does exert a force on the ball and pushes it back. So it's the air resistance, the motion of the air over the top of your car pushes the ball back and makes it appear like it's dashing away from you. Okay? Even though really it's moving forward still. To someone who's looking at this happen on the motorway, you know, if you shouldn't do this, but if you litter out the side of your car on the motorway, it looks like the rubbish zooms off behind you when you're moving at 70 miles per hour. But it's not zooming away from, you know, really it's not zooming backwards. Someone stood on the side of the motorway would see the rubbish go forwards, just it will go forwards and slow down quickly so it looks like it's going away from you. Because you keep moving at 70 miles per hour, the rubbish you throw out the side of your car slows down to 50, then 40, then nothing. So it looks like it zooms off behind you, but to someone watching it from the outside of the car, it still goes forwards. It just goes forwards less quickly than you do. Okay? Did you have another question at the back? Did I see a hand? No? Okay. All right. Super. Okay. So Galilean relativity. So we've defined these inertial reference frames. Let's talk about the principles of Galilean relativity. So Galileo tells us that in an inertial reference frame, so in a reference frame that is not accelerating, so from the point of view of someone who's moving at a constant velocity, all of Newton's laws are obeyed. Now, I'm putting a slightly ahistorical phrasing on this because obviously Galileo doesn't know about Newton's laws, so he describes it in a slightly different way, but this is the way I'm going to put it. So Galileo tells us that the laws of mechanics, the laws of how mechanical things move, Newton's laws, are obeyed in an inertial reference frame. And if you want to work out, you know, how fast something is moving in someone else's reference frame, you just add up the speeds. So say, for example, Alice throws the ball at VA, the velocity of the ball that Alice throws it with. Bob runs towards her at a velocity u, inwards towards her direction. The speed VB that Bob sees the ball having is the sum of those velocities. The speed of the ball that Alice throws it at plus the speed Bob runs at Alice. Okay? That's the second thing. The third thing, which is going to sound extremely obvious, is that the watch Bob has on his wrist and the watch Alice has on her wrist tick at the same speed. 1 second for Alice is 1 second for Bob. Again, that sounds obvious, right? That's what we expect. My watch doesn't change unless it's faulty compared to your watch, depending on, you know, it doesn't change whether I'm on a train and you're not on a train. There's no difference there. But we will see that is not necessarily the case in Einstein's relativity. So skipping forward about 200 years, we come to James Clerk Maxwell. So this is a Scottish physicist. I think was based in Glasgow, I think. And he's working out how magnets and electrical currents interact with one another. So he writes down a set of pretty impenetrable equations. So there's a couple of them here I've written down from his original paper, describing how magnets can influence electrical currents, how electrical currents can create magnetic fields, how these two things interact. Okay? So crucially, he outlines how a changing magnetic field can create a changing electric field, and vice versa. So a magnetic field that is sort of jiggling will create a jiggling electric field, and a jiggling electric field will create a jiggling magnetic field. And you can kind of see how this is a self-perpetuating thing. So a couple of years later, his original super complicated 26 equations are condensed down by this guy here, Oliver Heaviside. So this happens in about 1884. So he invents a new mathematical language to write down these equations. So there's a lot of stuff encoded in here that I'm not describing. There are things that these symbols mean, but nonetheless it's a much simpler form of writing the equations. He's broken it down into just 4 from Maxwell's original 26. Now, if you take these 4 equations from Maxwell and Heaviside, here I've denoted an electric field in red and a magnetic field in blue. Remember, the idea that Maxwell conveys with these equations is that a jiggling electric field makes a jiggling magnetic field, and a jiggling magnetic field makes a jiggling electric field. Now, if that jiggling continues and self-propagates, we form what is called an electromagnetic wave. That is a wave of oscillating electrical field, creating oscillating magnetic field, and so on, self-propagating. So you do some maths with these equations. You figure out if you had this self-propagating phenomena of electrical field making magnetic field, making electric field, and so on, you find mathematically there's a solution in there that appears to be a wave solution. Not only do you find that it's a wave solution, you find it's a wave solution that can only have one speed. Okay? The one speed you find it to have is this number here. Ooh, this number here, my head's in the way. 300 million meters per second. And this is a number that has been familiar to physicists for a couple of hundred years. This is precisely the speed of light. Okay? So this is really remarkable, actually. We have theoretical equations that describe the way that electrical and magnetic fields work together. We do some mathematics to them, and we find that they predict a phenomena, the phenomena of an electromagnetic wave propagating through space at 300 million meters per second. That number 300 million precisely matches another phenomena we know exists, which is light. We know light moves at 300 million meters per second. And physicists look at this and think, my gosh, we've predicted that light is an electromagnetic wave. This is exactly the speed of light. It reproduces what we've seen, what we've measured about light, but now we understand it in a completely new way. So light is an electromagnetic phenomena, the sort of periodic oscillation of electric fields and magnetic fields. And this is one of the things that if you study physics, when you see this, I saw this in my first year of university, and it's one of the things that just takes your breath away as a physicist. It's the perfect example of unknown phenomena, mysterious phenomena, in this case light, being explained by abstract mathematics, and that abstract mathematics perfectly matching what it is we see in the real world. This is one of the reasons I became a theoretical physicist, is because, it's astonishing how well mathematics, the things invented by humans, in a completely abstract sense, can bring you into contact with real stuff in the real world. I can't convey my excitement when I first saw this. This was one of the things that really actually quite almost sadly changed my life, seeing this come out on a blackboard. But it's a remarkable result. So light is an electromagnetic wave. That's the conclusion. So Galileo has a problem. If we try to apply Galileo's idea of relativity, that velocities add up. When you move towards each other, your speed looks higher. All the laws of Newtonian physics are the same in any inertial reference frame. Clocks tick at the same speed. If we apply this to Maxwell's equations that have just predicted light is an electromagnetic wave, we reach a problem, okay? So recall Feynman's golden rule. If your theory does not precisely reproduce or explain what you see experimentally, it's not a good theory. So the thing I didn't, I think, mention here properly is that if you try to apply Galileo's theory of relativity to electromagnetic phenomena, you reach inconsistencies. You find things that don't make sense. The left side of your equation no longer matches the right side of your equation. Things go completely wrong. And if your theory doesn't agree with the things you see in reality, it's not a good theory. So something is amiss, okay? So if your theory is insufficient to explain your experimental observations, it's not a good theory. So, considering that Maxwell's equations are the sort of newer law of physics, now it's not always the case that newer means better in physics, but Maxwell's equations are very highly tested. Not only are they highly tested, they're very practically useful. These are the equations we used to develop telegraphic communications, the electrical revolution, of the 19th century, all comes down to Maxwell and his understanding of light, electricity, and magnetism. So, a couple of years later, a very bright young man called Albert Einstein publishes a paper, and in this paper he reconciles Maxwell's equations, the description of electrical and magnetic phenomena, and light as an electromagnetic wave, with the concept of relativity. The idea that, again, moving at a constant speed should be indistinguishable from not moving at all. Being in an inertial reference frame, you shouldn't be able to tell how fast you're moving. So, Einsteinian relativity. These are the three laws of Einsteinian relativity as opposed to Galilean relativity. So first of all, Einstein extends this idea, and he says not only is it just Newton's laws being obeyed in all inertial reference frames, it's all laws of physics, including the electromagnetic, not just force equals mass times acceleration, Newton's three laws, there's more. Now, a consequence of this first law, this first postulate, is that the speed of light must never change for anyone, ever. Okay? So the speed of light, remember, he derives, not Einstein, but Maxwell, derives from his own laws of electricity and magnetism. So this is a law of physics, that the speed of light is not changing. That's a prediction of Maxwell's equations. Now, if we think about a consequence of that, if the speed of light is not changing, say, for example, you shine a torch at someone. The light leaves the torch at 300 million meters per second. Assume now that Bob runs towards Alice at 100 million meters per second. How fast do we think the light should hit Bob? Who wants to give me an answer? Yeah? Well,
Before you said to add them up, so wouldn't it be 400 million meters per second?
400, right, yeah. Whoever said 200, we're adding them, not subtracting them, because they're moving towards each other. Yeah, you would think 400 million. If I threw a tennis ball at you at 300 million meters per second, first of all, you'd be vaporized, because that carries more energy than the inside of the sun. But you would think, if you run towards this at 100 million meters per second, the two would appear to be traveling at 400, okay? But it turns out this is not the case. No matter how fast I run at this beam of light, it will always appear to move towards me at 300 million meters per second. Okay? This is the part that makes absolutely no sense to our intuitive understanding of how velocities add up. If someone's driving towards me at 30 miles per hour, I'm driving towards them at 30 miles per hour, we're driving towards each other at 60 miles per hour. What this is saying is that if I fire light at you at 300 million meters per second, and I move towards you at 100 million meters per second, the light does not get any quicker, nor would it get any slower if I was moving away. Okay? This is the bizarre part. This is the part that doesn't make intuitive sense because it's different to the way that we understand things on our length scales at the speeds we can move at. Okay? Any questions at this point? Yep.
I didn't understand. Is it because it's light, or is it like if you can launch something so fast that is not light, so it's not electromagnetic?
It's
So
yeah.
is Einstein still correct? Like if you have a car, but it's
Mm.
impossible. But if you could imagine that
Yeah.
you can, with some nuclear power, whatever, you can speed it up at
to near the speed of light, to that speed. Yeah.
I don't understand. Is it because his light is special, or is it because it's too fast, so then laws don't apply anymore?
It's a really good question. So light is special. So the first postulate that the speed of light is the same, no matter who you're asking, no matter who you ask, no matter how fast they're moving relative to the source of the light, that's the special thing about light, because it's Maxwell's equations of electromagnetism tell us the speed of light is a constant. And in order to reconcile that law with relativity, Einstein says the speed of light never changes for anyone. Now, you ask, would it be different if, say, a car traveled at this speed? Well, first of all, a car can never travel at this speed because nothing can ever travel at the speed of light. Light is special because it is the only thing, well, let me say that again. Light is special because it is the fastest thing in the universe. Okay? It has no mass. So light rays don't have any mass. So think about Newton's second law. If it has no mass, you sort of any force you. Well, sorry, no. This is a terrible explanation. Let me rewind. So light travels at the speed of light, which is a very cyclical argument. And it's special because that is the fastest speed anything can travel with. Okay? Anything that has no mass, such as light, will travel at that speed, 300 million meters per second. Okay? Without stopping. It might bounce off of things, but if it's moving at that speed. Anything that has mass can't really even get close to this speed. The reason that things like a car or a person can't actually get close to 300 million meters per second is that as you speed up, you get heavier. Your mass changes. Now, when your mass changes, to accelerate, you need a bigger force. So every little bit of extra speed you get a little bit heavier, and therefore you need an even bigger thrust to push you forward that extra bit of speed. And you'll never catch up. You'll never manage to get up to the speed of light, because by the time you're just a little bit away from it, the force you need is sort of infinite. It's an enormous amount of force needed. So the other part of your question is, well, what if, say, instead of shining light at 300 million meters per second, I fire a pellet or something at 299 million meters per second? Would it still be the case that that would, again, look at like 299 million meters per second? Well, no, it would increase. But it wouldn't increase to 399 million meters per second. Because what Einstein's relativity tells us is that the Galileo's idea of adding up the velocities is good when the speeds are not too high. If the speeds get close to the speed of light, Galileo's formula doesn't work anymore. And Einstein replaces it with a different, slightly more complex formula that does work and ensures that nothing will ever travel faster than the speed of light, no matter how fast the two things move at each other. Okay? Do you have a question at the back? Yep.
Let's say if a person could go at the speed of light, right?
Yep.
If they had to talk to them, like, right? How would it, if you were the speed of light, right, and you were running away from a torch,
Yeah.
how could it never reach if you're also at the speed of light? Because it would go at the same speed, but to you, it would still reach faster than the speed of light.
Well, the point is you can never travel at the speed of light. That's the. but you can't. Sorry, say again?
How fast does a bullet travel?
Oh, I don't know. Off the top of my head, I don't know. Say 100 meters per second, I would guess. So about
It's about 800 miles an hour.
800 miles an hour. So yeah, that's probably then about 100 meters per second, roughly. To 100 to 200, something like that. Yeah. So you can never travel at the speed of light. You can travel, if you could get very, very close to the speed of light, 99% of the speed of light, all of what I've said would still apply. If you fire a torch backwards, away from the direction you're moving, it would still go at the speed of light from your point of view. And from anyone standing behind you not moving, it would still hit them at the speed of light as well. Yeah, one more. Mm-hmm.
But from your point of view, you don't know if something's going at 399 miles per hour, or if it's going at, you can't tell if it's going just before the speed of light or if it is the speed of light, because our eyes aren't good enough to tell how fast something is going. So from us perspective, if something was going at say 299 miles per second, yeah?
Right.
Then you wouldn't be able to tell if it was 990.
Well, you certainly can't eyeball it because it's quite a hard thing to eyeball. But we have equipment that can measure it and can measure it very accurately. So we have devices that can do it. But you're right, we can't just look at it and tell. Yeah. Did you have a question in the middle? Did someone put their hand up? Oh, you have a question? Yeah.
As you speed up, the number of cells in your body remain the same.
Mhm.
Gravity remains the same. Why do you get heavier then?
So it's not so much that I know I said weight, but really it's your mass changes. So mass and weight obviously different. If you have mass if you're in empty space where there's no gravity. Mass is about how much stuff you contain in your body. And you're right, when you move at a high speed, you don't get any more stuff in your body. You don't have any more billions of cells. But nonetheless, your mass is larger. Because the measurement of mass is a relative measurement. When you measure the mass of something, if you measure it when it is stationary in front of you, the mass of a proton that is stationary in front of you is different to the mass of a proton when it is moving. So it's that every subatomic particle that makes up your being has a different mass when measured at higher speeds than it does measured at zero speed. So it's sort of extending the idea. Remember we said velocity is relative. Depends who you ask, how fast they're moving. The measurement is not absolute. Mass is also not an absolute measurement. It's just that all the masses we write down, if we write down the masses of all the fundamental particles, these are by definition measured at zero speed in a lab, for example. But if you measure them at a different speed, at a high speed, they have a different mass.
And that's been proved experimentally.
Mm-hmm.
Really?
Yeah. Yeah.
Why?
The why is hard. The what is that happens. The why is, again, it's sort of like, well, why does the velocity change when I run at something? Why does the velocity look different? Because it's a relative phenomena. It's easier to picture the velocity because, we know in Galileo's terms, we just add them up. The 5 and the 2 means the ball hits me at 7. The calculation and the proof that the same happens to mass is much more harder to get your head around. But we've done the calculation, we've tested it, and it works well. But it's a hard one. Yeah, at the very back, yeah. Okay, yeah, sure.
If you're gaining mass when you're not gaining size, wouldn't you, if you go really fast, just become a black hole?
Maybe. I don't know. I suppose, yeah.
And maybe that's the reason nothing, because it would just become a black hole. Even if you did put in enough energy to go at 99% of the speed of light, you'd probably just become a black hole.
I don't know. I don't know, to be honest. There's a phenomena called a Kugelblitz, which is
So it's so hot that it...
exactly. You have enough energy that enough energy in a small enough space that it forms a black hole. So perhaps by that reasoning.
You can do it on the energy side as well.
Yeah, that's right. That's exactly right. So perhaps, yeah, if you're traveling at that high speed, the energy of your motion would be so large that it might collapse you. I'm not entirely sure. I'd have to do the calculation. Yeah, at the back. Oh yeah, I'll come to you after. Sorry. Yeah.
Is the
meters per second. Meters per second.
But if it's 300 million meters,
Yep.
if you have a really bad torch, right, it can't even go 300 million meters, meaning you can't measure that.
Even the worst torch goes at 300 million. All light goes at 300 million. You can't make it go any slower.
But if it can't go that many meters, then that means it's not 300 million.
Well, that's different. That's about how far the light goes, because light rays can hit molecules in the air, and then they stop moving altogether. They stop existing. They get absorbed by molecules in the air, and then they don't travel any further. But as long as they are traveling, they go at 300 million meters per second. They might stop. They might hit something and get absorbed by it. But it's not about how far they travel. It's about how fast they travel. Does that make some sense?
Oh, I just thought because like a meter
Yeah.
is that long, so I thought
Yeah.
if you go 300.
I see. So it's sort of like if it could travel for a second, that's how far it would go. But it might not be able to travel for a full second because it might hit something before it gets that far. That's a good question. We'll have one more at the back. Yeah.
I'm thinking about the electromagnetism.
Yeah.
Before.
Yeah.
There's electricity in the brain, so presumably it's really dangerous to put magnets near the brain, or strong magnets anyway, because it would mess up the electricity.
We put extremely high magnets on the brain in an MRI.
That's all right.
Yeah, the other thing is that it depends on the size of the currents inside of the force on a current depends on the strength of the magnetic field and how big the current is. And I would assume the currents in the brain are extremely tiny. So even in a strong magnetic field, it's a very small force acting on them. Yeah. Okay. Yeah.
Yeah. So where's the classification of light? Is it to do with the wavelength? Is it to do with it not having mass?
Yeah, so you're talking about like the fact we've got X-rays, gamma rays, all the different kinds. Yeah, that's about the wavelength. So, it's like a water wave. You've got peaks to a water wave and troughs to a water wave. Light is the same. You have peaks, and the distance between the peaks we call the wavelength. So the longest wavelength are things like microwaves, radio waves, and the shortest wavelength are things like gamma rays and X-rays. They're very high energy, very short wavelength.
But is it to do with the mass of the classification that they all travel at the speed of light?
So they all have zero mass, but they have different energy, is the thing. Yeah, the higher, the shorter the wavelength, the higher the energy. Yeah. We'll take one more and then we'll move on.
Do radio waves travel at the same speed of light?
Yeah.
I believe they do.
They do indeed, yeah. Yeah. Now, the speed of light, so if you're learning sort of physics in school, you might hear about something called refraction, which is about how light bends when it enters a different medium. If you shine a ray of light into the water on the surface of a pool, it will stop moving at the angle you shone it at, and it will bend slightly when it hits the surface of the water, when it penetrates into the water. Now, the way we explain that is we say the light slows down when it goes into the water. That's a little bit of a fib. So I'm not going to talk about what actually happens because it's a bit more complicated, but I just wanted to make that clear that it's a little bit of a fib that the light slows down when it hits the water. It still always travels at the speed of light, okay? Okay, we've got to get through, or else we're not going to actually get to any of the relativity stuff. So the last of these three laws of Einstein's relativity. Clocks tick at different rates for different observers. This is the most bizarre of the three postulates, the three laws that Einstein presents. It's a consequence of the speed of light not changing. In some sense, it makes a bit of intuitive sense, right? If I'm saying that when I shine a torch at you and you run towards the torch at a super high speed, you don't see the light ray travel at any different speed to the speed it would if you were standing still. For that to be the case, something has to change about the way you measure time, about your perception of time. Okay? If you're running towards this light ray, you would think about, you would think that it would be traveling at 400 million meters per second if you travel at 100 towards the light ray. But the fact that you don't means something about your perception of time is changing. But I want to be very careful about how I use this word perception of time, because it's not a trick. It's not something that's wrong with your clock. or something that's wrong with your brain or how you are looking at things. This is a real phenomena. For something moving at a high speed, close to the speed of light, you know, plants will germinate quicker. Grey hairs will appear at a different rate. You know, you will age at a different speed. It's not just about perception of time and clocks. It really is the actual nature of time changes when you move at a different speed. Yeah? One more question, yeah?
The reason you can't escape a black hole is because of that. In a black hole, space and time are inverted. So,
Sort of.
to get out of it, you have to go back in time. And if you travel faster than the speed of light, you go back in time, which is where it breaks down. That's why you can't go faster than the speed of light.
The way I think about a black hole is more like imagine you're in you know, a very fast-moving stream, and the water in the stream is moving so quickly that no matter how fast you paddle relative to someone on the bank, you're still moving inwards down the stream. You're still moving towards the black hole, no matter how fast you move. And you're limited in how fast you can move because you can't go faster than the speed of light. So I see what you're saying in some sense. If you wanted to get out, you'd have to go faster than the speed of light. But nothing can go faster than the speed of light. Yeah?
You can't go faster than the speed of light. That's why it's impossible to leave the event horizon.
Yeah, that's one way of thinking about it. Yeah. Okay? All right. So let's describe this first phenomena, this first key phenomena in relativity. So this is called time dilation. As we've said, the idea is that time ticks at a different rate depending on how fast you're moving. There's no such thing as absolute time. Okay? So suppose now Alice has a clock. This is sort of stationary in her reference frame, and she sees Bob move with his clock at a very high speed. Now, there's a formula. So the formula, by the way, just if you want to see this, quite a few years ago, I published a YouTube video deriving this formula using just Pythagoras' theorem, because actually the maths is not that complicated. It's the conceptual part that's complicated, if any of you wanted to take a look. So the formula. Sorry, before we get to the formula. So Bob is moving along. In his reference frame, he looks down at his clock. His clock ticks at 1 second per second. You know, it looks like 1 second to him. It's 1 second on the arm of his clock. Okay? Now suppose Alice is looking at Bob's clock as he moves. Now, from Alice's point of view, Bob's clock will appear to tick more slowly. Okay? Not only will it tick more slowly, but you know, Bob is shouting back, "You can't catch me," to Alice. If he's moving quick enough, his speech will appear to be sort of drawn out and longer. Okay? So Bob's clock does not tick as fast as Alice's clock when she observes how fast his clock is ticking. And again, this is not just a problem with the clocks. If there was a plant, you know, on Bob's spaceship, if he was on a spaceship, the plant would grow more slowly. Bob would age more slowly. Okay? Everything would happen as if time was ticking more slowly for Bob, as seen by Alice. Okay? So, why do we not see this in our everyday lives? You know, for example, why is it not the case that if I'm moving at a very high speed and I'm on the phone to you, my voice doesn't become slower and it sounds like I'm working in slow motion, right? Why is that not the case? Well, we have to think about the equation. So this is the equation for time dilation that describes how a tick on a clock for Bob compares to a tick on the clock that Alice has. So we're dividing it by this square root of 1 minus the speed Bob moves at and the speed of light, both squared. Now, the speed of light is extremely fast, 300 million meters per second. Okay? The speed of Bob is far, far slower. So unless you're moving at a speed that is comparable to the very high speed of light, this phenomena is impossible to observe. So I meant to go through a calculation, but I realized that I made an error on it. So I'm not going to go through that calculation, but I'll just sketch you through roughly what it was, because I don't want to present something that's mathematically incorrect. But I was looking at the Parker Solar Probe, which is the fastest moving thing humans have ever built, because it's falling towards the sun basically, so it's getting pulled extremely quickly. And I did a calculation, but again I made an error in it, so I'm not going to show you it. That showed that even at this extremely high speed of something like 190,000 miles per hour, the time difference between a clock on the Parker Space Probe and a clock on the Earth is less than 1/10 of a nanosecond. So a 100 billionth of a second, every second. That's how much the clocks go out of sync. So it would take, about 10 billion seconds for the clock on the space probe and the clock on the Earth to get 1 second out of sync. And that's something that's traveling at 190,000 miles per hour. So that roughly corresponds to, it would take about 2 months for 1 second of difference between the two clocks, even at that extremely high speed. So unless you're going right at the speed of light, right up to close to the speed of light, this phenomena is not observed. That's why we don't see it in our everyday lives. It's not that it's not happening, but it's that it happens in such a tiny, tiny way, you only see it in these extreme scenarios of very high speeds. Okay? Yeah?
Not just that, if he ran away, say, from 20 miles per hour, and then she decided to catch up with him at 20 miles per hour, the clocks would go back to sync anyway.
Then they'd be in sync, yeah.
Yeah.
Yeah, that's right. Because there'd be no relative motion between them. That's right. Yeah, at the back?
So what is faster, the speed of sound or the speed of light?
Light. Light by a long shot, yeah. That's why you see lightning flash before you hear it. It's about 1 million times faster. So sound is about 300 meters per second. Light is about 300 million meters per second. Okay?
So when
Yeah.
you see lightning flash,
Yeah.
that doesn't take many years.
Well, because it's not that far away. So it's that you see it flash in like 1 billionth of a second, and you see it and you hear it flash in 100th of a second, which is still a very short time. So it's it's 1 million times slower, but it's still very, very quick. Does that make sense? Yeah?
How do Alice and Bob meet again at the same point in time? Because presumably, so if Bob's running away really fast, his clock ticks more slowly, and then they meet. But when they meet, they must be agreeing on the point in time at which they meet.
Yes.
How does it work?
So they agree on the point of time at which they started, before Bob ran away. They agree on the point of time at which they meet, but they disagree on how long it took them to get to between those 2 points.
Okay, so there's just literally more time in Bob's world, effectively.
Less time in Bob's world. Yeah. Yeah, that's right. Yeah.
Devil's advocate. This can't be proved experimentally. It's impossible, isn't it?
No, it has. It has
The
been.
thing,
Yeah.
I was just going to say that Freeman said if you can't prove it experimentally, then go back to your theorem, it's wrong.
That's right, but we have proved this experimentally. No, you're quite right to point that out. So we prove it, first of all, we prove it, I think I've said this a couple of times before, you prove it every time you use GPS, because for GPS to work, you need super, ultra powerful, ultra accurate atomic clocks on GPS satellites to make comparisons with how long it takes to bounce a signal from your little GPS receiver between the satellites. So you need these super accurate clocks. Now, there's another sort of slightly separate time dilation phenomena which occurs due to the presence of a gravitational field. So gravity also changes the way time ticks. Okay? So the clocks up in the satellites are further from the Earth's gravity. They have a weaker gravitational field, and so they tick a little bit quicker. And we have to do a correction because after so many days, so many months, there'll be a nanosecond out of sync. But for GPS, that nanosecond out of sync is a very big error in where your position is. So we have to use Einstein's formula and correct the clocks. Manually, we have to tune them, turn them back. Okay? So we test it every time we do that. But there are lots of ways. Everything in astrophysics, cosmology, particle physics is built on the framework of Einstein's theory of relativity. So every time we test basically any idea in physics that has come later than 1905, we're testing Einstein's theory of relativity. Okay? Okay. Yeah, one more.
Was it said that the astronauts returning from the moon came time?
They would have
I
done.
can't remember. But
Yeah, they would have done, because they spent time away from the Earth's larger mass and on the Moon's lower mass, lower gravity. Their clocks would have ticked slightly quicker. Yeah. Okay. Yeah, one more.
They also went faster, like when they were on a rocket, they would move faster. So
Oh, yeah.
that would also count. But it would probably only be like a billionth of a second.
Yeah, super tiny.
Nanosecond or something.
Exactly, super tiny. So
Unconceivable.
exactly. Yeah, one more at the back.
So about that thing about like the clocks and like aging and stuff.
Yeah.
Let's just say someone had two twins.
Aha.
At the exactly the same time.
Mm-hmm.
And you forced one twin into a rocket.
Yep.
That went around like in space.
Yep.
Like speed of light.
Yep.
For let's just say 50 years.
Mm-hmm.
And the other twin.
Mm-hmm. Was just home on Earth. Yeah.
Just had a normal life. When that twin came back from space, wouldn't that twin be maybe something like 14 or 15 years old, and then that other twin would be something like 50?
That's exactly right. Yeah, because they're traveling at a very high speed, their clock ticks less quickly than the people on Earth. So if they fly off around the sun for 10 years, they might come back and their identical twin on Earth might have been there for 30 years. There's a difference. So suddenly they'll no longer be identical. One will be 20 years older. That's exactly right. We'll talk more about that kind of similar time dilation effect when we talk about black holes next week. Okay? We're going to move on though, or else we're going to miss some good stuff. So forwards time travel. Forwards time travel is perfectly possible. Okay? There's nothing wrong with forwards time travel. So we can imagine a kind of time machine where, for example, we have a train that's built so that it runs along the equator of the Earth. And let's say that it runs at 190 million meters per second. So this is less than the speed of light at 300 million, but still very, very fast. In fact, it's about 63% of the speed of light. So relativity matters here because you're moving at a speed close to the speed of light. Okay? So at this speed, it would take only 0.2 seconds for this train, to whiz around the entire Earth. So if you're stood on the platform of a station looking at this train go past, you'll see it make a complete rotation and go past you 5 times every single second. So very, very quick. But from the point of view of the passengers on the train, this hasn't taken 0.2 seconds, it's taken 0.15 seconds. So 0.05 of a second less time has passed for the passengers on the train. And so in some sense, every time they circle around the Earth, they travel forwards in time by 0.05 of a second compared to everyone else on the Earth, not on the train. And if you run this for long enough, say, for example, it takes 10 years as measured by the people on the platform watching the train go by. They see the people on the train for 10 years, which given the state of our rail system is not an unreasonable journey time. For the people on the train themselves, it takes less than 10 years. For them, it takes 7 years and 9 months. So they have sort of speed run. They have gone ahead by 2 years and 3 months compared to everyone else on the Earth. They will be, again, if you have 2 identical twins, one on the train, one not on the train, the one who was not on the train will be 2 years and 3 months older than the one who was on the train. Okay? So forwards time travel is easy. We can do that. You can spin very quick around the Earth. Obviously, this is an unachievably high speed. This is about 1,000 times faster than the Parker Solar Probe, which is the fastest thing we've ever built. And again, it's only fast because it's falling towards the sun. It's not fast because we're firing it or something. Or you can go hang out near a black hole. And again, we'll talk about that next week. What about backwards time travel? Is backwards time travel possible? Could we go back and see the dinosaurs or have tea with Jane Austen? Could we do any of these things? Well, Einstein's theory of general relativity, his theory of gravity, which again we'll talk more about next week, predicts the existence of structures called wormholes, which connect distant regions in space by a throat that sort of extends through a higher dimension, again quite abstract stuff, to connect very distant spaces, which without the wormhole you would have to travel half the length of the universe to get to. It gives you a shortcut That means you can pass more quickly. But not only can it potentially connect different regions of space, it might connect different moments in time also. And Einstein's general theory of relativity doesn't rule out the existence of these wormholes that might extend backwards in time. It's thought, though, that once we come up with the improved version of Einstein's theory of gravity, a theory of quantum gravity that includes black holes, the singularity of black holes, and brings together the ideas of quantum theory, that the conditions needed for these wormholes will be ruled out, and backwards time travel will die with that. That's what's thought. Yeah, did you have a question?
In quantum physics, we know answers to physics, but positrons in a Feynman diagram, do they go backwards?
It's a bit of a mathematical trick.
Okay.
So yeah, in some sense, antimatter, like a positron compared to an electron, can be thought of as the same charged particle moving backwards in time, but it's a mathematical trick. Exactly. It's about balancing the equation. It's not really going backwards in time. That's a good question, though. Okay. Any other questions at this point? Yep.
Wasn't it that, like, if you had a spaceship traveling towards Earth
Uh-huh.
really fast, they'd be able to, like, communicate back in time, and maybe the other way around. So I remember watching a video about, like, if you're going fast towards something, you can if you had, like, a magical Wi-Fi connection, you'd be able
I wish I had a magical Wi-Fi connection.
You'd be able to talk to, like, Stephen Hawking.
Well,
And also people in 2060.
so there's some sense.
Which way you travel.
So right. So for some observers, what we perceive of as the past has not happened yet. You know, the example that's often given is if you think of a planet that is about 65 million light years away from us, meaning, you know, the light takes 65 million years for them, from us to reach them. They would look at the Earth and they would see these guys. They would see dinosaurs. So for them, that is the present. That's the present on Earth as perceived by them. Likewise, if you're, when did Stephen Hawking die? 2017. So, you know, if you're like, 8 light years away from the Earth, you can listen live to him giving a lecture or doing a talk. And for you, that would be the present, and he would be talking to you what is live to you. Okay? We're going to move on because we're going to run out of time. Okay? So there's another phenomena that I just want to mention. I'm not going to say much about it, but we've discussed how time changes, how the duration of time is changed by relative motion. Okay? Faster clocks tick less than stationary clocks. So too, lengths change. So space and time in relativity get kind of muddled up and mixed about. And so time is sort of stretched, as we've discussed, but space is sort of squashed. So someone who is moving at a very high speed will be measured to have a smaller length by someone who watches them move at that speed. So when Alice sees Bob move at a very high speed, she will see him sort of squashed. She will see his length contracted. And I've put the formula down again just to again illustrate that the factor in this formula that tells us this happens is again a ratio of the speed of light. Meaning the reason, if I run away from you, I don't suddenly look skinny, is because I would have to move at near the speed of light for that to happen. Okay? Which is a little bit harder than dieting. Okay. So, simultaneity. Time is getting stretched, time is getting changed. Now, a consequence of that is that things that appear simultaneous to one person are not simultaneous to everybody. So a really simple example we can use for this is imagine you've got someone sat on the Earth who is sort of perfectly between two stars that are about to go supernova. Very far away, so it's not causing us an issue. And there's someone on the moon who is slightly closer to one star than the other. So for Alice, when these two stars go supernova, she's equidistant from both of them, so the light reaches her at exactly the same time. So she sees, boom, boom, they've gone at exactly the same time, these two stars. Bob, on the other hand, is slightly closer to one of the stars than the other. So the light that is traveling from the supernova to his eyes takes a little bit less time than the one on the right, because the one on the right has got further to travel. And again, we perceive something when the light of that thing happening hits our eyes. We don't perceive it instantly, okay? You have to wait for the light to hit your eyes to know that it has happened. So from Bob's point of view, he sees one star go supernova before he sees the next one go supernova, okay? So 2 events that were simultaneous for Alice are not simultaneous for Bob. Another example of how this can happen is if Bob is moving at a very high speed, so is on a rocket. If these stars, again from Alice's point of view, go supernova simultaneously, from Bob's point of view, sorry, we're not yet at Bob's, so from Alice's, again, the light, she's in the middle, they reach her at the same time. From Bob's point of view, even though he might be passing right on the top of Alice, so at this instant he is equidistant from both stars, one of them will occur before the other. The one that he's sort of pointing towards, moving towards, will appear to occur before the other one, okay? So the relativity of simultaneity changes which order these events happen in. They no longer occur simultaneously. So the reason I illustrate it with this separate example is just to say it's not just a case of your position in space affecting whether things are simultaneous or not. It's also about how quick you're moving affecting whether things are simultaneous. Okay, that's a bit of a harder one to explain. The case of the moon and the Earth, I think this makes sense. He's closer to one, so the light from it hits him sooner. Okay, this case is slightly harder, and I've not derived this, I'm just sort of telling you about it, which is that if he's moving towards this one also occurs from his point of view before the one behind him, even if he's in the middle of the two. Yep.
I think it gets back to that tennis ball thing you were saying, that if you throw a tennis ball at him, that ball to him is coming quicker. Because he's going towards it, the light from that is coming to him quicker, but the other one's not.
No, it's not. It's not. It's still going at the speed of light. That's the bit that's weird. The light from both supernovae is still going towards him at 300 million meters per second. The one over here is no faster. The one over here is no slower.
No, I said he perceived it, not he actually was going faster.
No, he still doesn't perceive it. He still perceives them as just going 300 million. So the reason for this is a little bit more complicated, but it's not a case that the light is coming quicker and slower from behind. It's about it's a little harder to demonstrate, okay? So for now, I just want you to keep this in mind because I want us to apply this in the last 5 minutes. So I want you to imagine we have a tunnel and we have a train. And for some reason, this tunnel has 2 doors either side, and these 2 doors are going to kind of chop down. The system's rebooting or whatever for the doors, so they're going to very quickly slice down and then reopen, okay? And Alice, who's operating the train tunnel, has left it too late, and she has to restart it right now, or else the system's going to blow up or something. And Bob is on the train moving towards the tunnel. So right now, Bob's not moving, sorry. This is just a comparison of their lengths. So they have approximately the same length as one another. So this is quite risky, the tunnel's going to close and it might chop off the end of Bob's train or chop off the front of Bob's train, depending on how far into the tunnel he is. So let's think about this from Alice's point of view. Alice sees Bob's train rushing towards the tunnel, but because the train is moving, Alice looks at it and she says, oh, it's moving at very close to the speed of light, so its length contracted, it gets squashed, because it's moving at high speed, okay? So Alice is thinking, this is great. The tunnel's, a length I've called L0, L0, and the length of the train that Bob is on has been squashed because it's moving. It's now a length L that is less than L0. So that means Bob's train can fit fully inside the tunnel when the doors slam down. No problem. Alice is happy. Okay, and then they open and Bob's train leaves. From Bob's point of view, now, remember, relative to Bob, he's moving along at constant speed. He feels like he's standing still in his train, and it looks like everything is rushing towards him. Like if you're driving along in your car, the car in front of you, if you're not braking quick enough, rushes towards you. That's how it feels to you rather than you rushing towards it. That's what it looks like to Bob. It looks like the mountain and the tunnel are zooming towards him. And again, who's right? No one's right. They're both moving at constant speed. No one is to say that the tunnel is still and Bob is moving towards it. It's just as correct for us to say Bob is still and the tunnel is moving towards him. Okay? In relativity, as long as they're moving at the same speed, we can't make a definitive statement about who is absolutely still and who is absolutely in motion. That doesn't make sense in relativity, okay? But Bob is a bit worried because if the tunnel is moving towards him at a speed v, the length of the tunnel is squashed. The tunnel appears shorter. So he's quite distressed because, these doors are going to slam down and I've not got enough room to fit my train inside when they close down. So he's worried, okay? So the thing I want to point out is that from Alice's point of view, these doors closed simultaneously. They slammed shut, okay? Now, after Bob passes through the tunnel, whether he gets cut in half or not is an absolute fact. Him and Alice can compare notes. If Bob is, sitting in the smouldering wreck of half of a train, we know he didn't make it through. If he's fine and moving on to Liverpool Street or wherever, we know he made it through. These are absolute facts, and people should agree on absolute facts and absolute events, okay? We don't agree on things like the duration of time. We don't necessarily agree on the length of something, but we agree on facts like that, on events, okay? So, because simultaneity is relative, the first door, the one over here, from Bob's point of view, appears to close before the second one, okay? So it chops down and lifts up before Bob passes that far into the tunnel. So he's not chopped by the first one, by the second one, the one over here. He moves towards it. It flashes up. And this one, remember, has not closed yet. Okay? So in Alice's frame, the two gates crash down simultaneously. In Bob's frame, boom, boom. They're not simultaneous. One comes down before the other. So Bob, again, is not squashed. He's not, it's not that he is saved because his train is shorter or because the tunnel is longer, but it's because the simultaneity of the closing of these gates that would chop him in half, or into three rather, that Alice perceives are not simultaneous in his reference frame. So he is saved for a completely different reason. So he manages to pass through the tunnel unharmed, and they agree on that event, as they should do. So for Alice, she agrees that Bob lives because the two doors, boom, come down when he's fully inside the tunnel. Bob agrees that he lives because the tunnel doors sort of don't close simultaneously. If I do it quick, you can see it as a little animation. They sort of move out of sync, and they both manage to miss him because then that simultaneity of those events of the gate closing is relative, and so he survives. Okay? So we're running out of time. If anyone has questions, you can come up at the front, but just before we finish up, I just want to point out that there's another talk next week, same time, same place, where we're going to talk about black holes. If you came to the talk I gave a couple of months ago on black holes, we're going to talk about some new stuff as well. So even if you came to that, you'll still get something from this one. But we're going to talk all about Einstein's theory of gravity, how gravity and black holes distort time in a similar way to how we've seen for moving trains and moving other objects. And lastly, if you want to see the lecture slides I've used, if you want to check anything, check my calculations, you can get them from my website. The link there is cosmicconundra.com. There's also, I know I linked the YouTube video where I derived the formula. You can find that as a link on these slides as well. Okay? I've not uploaded them yet, but I will do when I get home. Okay? Okay, let's leave it there. Thank you very much.